Hi, my name is Avi Perlman, and this is Lab 3, the magnetic field of permanent dipole magnets. The purpose of this lab is to determine how much magnetic field depends on observation distance. In order to find this out, I utilized a bar magnet and a magnetometer app. The underlying goals of this lab are to compare empirical measurements to the Biot-Savart law equations for magnetic fields, as well as construct a computational model to create a graphic of these fields. Ultimately, I found my magnet's dipole moment to be 1.6273 amp meters squared and an N value equal to negative 3.25. The primary physics concept behind this lab is the Biot-Savart law, which expresses magnetic field. We can utilize the on and off axis forms of this equation in order to find the magnetic fields of a bar magnet at various locations. We also utilize the distance-dependent equation. Because n and k are constants, we can rearrange this equation to a logarithmic form as shown. To conduct this experiment, I first needed to determine the direction of the magnetic north by laying my phone on the table and rotating it until the x component was 0. Next, I set up my meter stick perpendicular to the magnetic north and found the magnetometer on my phone by locating the cross-section of the locations where the magnetometer reads the maximum x value and the maximum y value. Finally, I moved my phone along the meter stick to various locations, both on axis and at a 45-degree angle, to obtain the desired field values. While carrying out the experiment, I noticed the magnetometer is very sensitive to nearby objects like electronics that produce fields. I also observed the x component of the magnetometer increases as the phone neared the magnet. Finally, I realized that the field of the Earth must be accounted for and subtracted from the y component of the magnetic field for an accurate measurement. Here's the data I collected from my on-axis measurements. Utilizing the logarithmic form of the distance dependence equation, we can produce a graph and line of best fit for the data where natural log of r is on the x-axis and natural log of field's x component is on the y-axis. This equation helps us find k and n. Here we have that ln of k equals negative 14.938 and n is equal to negative 3.2471. We can utilize the n value we find from the curve to find that the percent error is 8.24% with reference to the expected n value of negative 3. We can also rearrange the equation for k to find that the magnitude of the magnetic dipole moment is 1.6273 amp square meters. Here's the data I collected off-axis at a 45-degree angle with the horizontal. Here I had to correct the y component by subtracting the magnitude of the Earth's magnetic field. I found the average perpendicular distance from the magnet to the cross-section of the rulers was 0.16 meters. I also found that the average magnitude of the net magnetic field was 5.62 times 10 to the negative 5th Tesla. Here's a computational model I created in Python. First, I found the magnitude and direction of mu. Subsequently, I created a function to calculate magnetic field that takes in two arguments, mu and r. It first finds the magnitude and direction of r, and then utilizes the Biot-Savart law to calculate the magnetic field. After that, I created 6 vectors for the observation locations, 2 on axis and 4 perpendicular to the axis. Next, I created 2 arrows to represent the magnetic field on axis, one at each observation location. I also created an arrow to represent the magnetic field for each of the 4 observation locations perpendicular to the axis. Finally, I created an arrow to represent the magnetic field 45 degrees from the axis at the observation location I found through experimentation. Here is the output of my program. As you can see, the orange arrows represent the on-axis field. These are aligned with the magnetic dipole moment. The cyan arrows represent the field on a perpendicular axis, and the purple arrow represents the field at 45 degrees from axis. When comparing the magnitude of the net magnetic fields between the experiment and the computational model, we see that the computational model has smaller x and y components. This may be a result of human error in the experiment, as well as external magnetic fields from objects in the surroundings. If I hadn't oriented my experiment to compensate for magnetic north and instead laid out my meter stick at an intermediate angle, all observations would be affected by the Earth's magnetic field. The x component of the magnetometer would be non-zero, and I would not be able to use it to measure the magnetic field that is perpendicular to that of the Earth. Additionally, the values of mu, k, and n would not be accurate. If I were to stick two identical magnets together end to end and run the experiment again, the direction of the magnetic field would remain the same, but the magnitude would approximately double due to the superposition principle. It would not double exactly, however, due to distance dependence.